happy to have Florent, Saclay, and Lenka Zdeborova speaking on statistical physics and computation in high dimension. The first lecture today will be given by Florent. Please go ahead.
All right. I am assuming that you can all see my slides, so I will start. Thank you, Nike. Well, it's a pleasure to give the lecture. Of course, I would have rather, it would have been much better to be in Simons reunited again, but next time, I guess. And anyway, thank you for the opportunity to present this set of notes. All right, so this is a series of 4 lectures every day in the next 4 days, given by myself and Lenka. And this is somehow a brief outline. So I will today discuss statistical physics method. All right, the lecture is called Statistical Physics and Computation in High Dimension. And somehow, this is not orthogonal to the rest of the lectures, but it's rather different. And it involves effort from a different community. So this first lecture will be, well, I hope clear, and we'll try to look on very simple problem in order to expose the ideas and the methods that have been used by this community of people, in statistical physics and mathematical statistics, and then trying to apply it to some problem in computations. Right, and tomorrow I will go into the heart of the subject. I will discuss computational and statistical phase transition. And once you will get the stage, then Lenka will give you perhaps more advanced and more recent results and also open problems that we are facing. Also, I want to add that I have a lot of materials connected to this course. They can be found here at this address. It's a page that I set up for a lecture given on these topics at Duke University 2 years ago. And thanks to our amazing TAs, we have very good lecture notes, exercise, and even Jupyter notebooks. And also, a large part of the material can be found in the review Statistical Physics of Inference, Threshold and Algorithm, that was written a few years ago by Lenka and myself. And it's an excellent reference for what I'm going to talk about. All right, so let's start. Today, Statistical Physics Method 101. All right, it's not really 101. I'm not gonna teach statistical physics, but you don't need to. I think what you need here is to have a dictionary about the vocabulary used in statistical physics with respect to what you use generically in computer science and more generically in probability theory. And this is what I'm going to discuss today. Okay, and I hope the material will be clear enough for everyone. Okay, first of all, I just want to mention that this idea of using statistical physics for problems outside physics is quite an old one. I mean, it started from the 80s, and we had really great scientists who initiated this line of thought. And in particular, there is this beautiful article written in '89 by Nobel Prize winner P. W. Anderson, when he was saying that these new tools that we are developing around the statistical physics of spin glasses might be very useful outside spin glasses, and it's a cornucopia. A lot of problems can suddenly be tackled with these techniques, and certainly, he was right, and that set of ideas kept us busy in physics and in mathematics in the last 3-4 decades, and I will try to discuss them today. Okay, so there are 2 types of problems that I will be discussing. And for the 2 of them, I will try to use statistical physics technique and try to avoid as much as possible statistical physics jargon, right? But I also want to introduce you to the jargon because this is, after all, what you will find in articles, so it might be useful. Anyway, so sampling. Okay, so some of the problems you can study with this technique are sampling problems, and for instance, Bayes estimation problems. And that will be something that will appear a lot in this set of lectures. So here is a type of problem that we are discussing. So let's say you have a generative model, okay, a probabilistic model. So X is sampled from distribution P of X that you know. For instance, it's a vector in d dimension, and then something complicated happened, and from x, you created y, which is, for instance, a vector in m dimension. And between the two, something complicated happened. But you have P of y given x, you have the conditional probability. Right now, y is your observation. You know the process, you know P of y given x. And the question is how to find a good estimator x hat for x. Okay, so this is a standard setting of Bayesian estimation. And if you want to do Bayes estimation, well, of course, you're using Bayes theorem, and you write the posterior estimation, P of x given y, just P of y given x, P of x over a normalization. All right, so the trick is to rewrite this as taking the exponential of the log here, and it doesn't make a big change, but suddenly you can write things with the statistical physics notation, which are extremely simple, right? Now, here, this quantity, we rewrite it here, and we call it the Boltzmann measure. And if we want to say that is one over z exponential minus beta h, well, we need to have beta equal 1, and h is minus the log of this quantity. Okay, this quantity is called an Hamiltonian in statistical physics for historical reason, but this probability measure is the same as this probability measure. Now, once you have this probability measure, you can define averages. Physicists, for some reason, do not use too much expectations notation, and they are really big fans of their angle notation. So these will denote averages with respect to that kind of measure. Okay, and this normalization here is usually called the partition sum. All right, so this is essentially the whole story. And if you study the Boltzmann measure, well, you're a physicist. And of course, there is a one-to-one mapping between these two. And this means that any Bayes estimation problem can be mapped into some kind of physics formalism. All right, the second type of problem that I will discuss and will be discussed in this set of lectures are minimization problem. Now, it goes basically in the same way. Let's say that you have a function that you want to minimize over a set of variables, call it S. You can call this a cost function. These days in machine learning, maybe perhaps you will use the word loss that you want to minimize. And physicists still will insist to consider the word energy or Hamiltonian. In the same way, you want to minimize this. Okay, and the way this is done, well, we can use again the Boltzmann measure. We can write the probability distribution, the Boltzmann measure of exponential minus beta h, or beta c, or beta l if you want to use the loss. We have still the same Boltzmann averages, the same partition sum. But now you realize that as beta is going to infinity, the probability measure will concentrate on the minimum of the cost function, if it is well defined. Okay, so using beta, which physicists call the inverse temperature, this allows you to probe different problems. Finite beta means sampling, and infinite beta means looking at extremizations, okay, minimum. And for instance, it's trivial to check that if you take the log of z and you derive it with respect to beta, at any finite temperature, this is giving you the expectation of the energy. And when you send beta to infinity, then you have the minimum, right? And this is already telling us that this object, the log of z, which physicists call the free energy, will be the fundamental one. All right, so now we have set up the notation. And what I want to do now is, before going to really interesting problem, instead to be looking at an extremely boring problem. It's a completely boring problem. It's really not interesting, but it has the following advantage. If I looked at this problem, I can present essentially all the techniques that I want to tell you about it that will be used in the next 3 lectures in the set of 50 minutes or so. So this is what I will be doing. All right. So look at the following problem. It's called the random fingernail model in physics. So we have n binary or Rademacher variable, if you want. So this binary variable can take the value plus or minus 1, and there are n of them. Now, this is our cost function. We call it Hamiltonian because we are physicists right now. And this is what it is. It's just this term, which is the sum of s divided by n squared, with a minus sign here. So if we want to minimize this, well, it's easy. What we need is to have these s's to have all the same sign, okay? All plus or all minus, that will be the trick. And we have this additional term here minus sum over I, hi, what physicists call fields, si. And these fields, these terms here are chosen randomly from a Gaussian distribution once and for all with variance delta. Now, of course, this term would like the variable to align with the direction of the h, while this term would like the variable to all have the same sign. And there is a competition between the two, all right? And the term random field is referring to this part. It's actually an extremely useful and important model in statistical physics. All right, so say now you want to minimize this function. Actually, minimizing this function is extremely easy. In fact, here this is a problem defined on a complete graph because you have the sum of si squared. But in fact, on any graph, minimizing this function is in P. There are many techniques that allows provably to find the ground state. So it's not a hard problem. Still, it will serve as a very good example for what I want to say. All right, so the real question I want to answer is this following one. Now, let's say that we are in I dimension. So n is going to infinity. Okay, this is the topic of Simon's meeting after all. And the question is, what is the typical value of the minimal cost when you minimize this function? Right? Or more precisely, what is the typical value of the minimal cost divided by n? And we hope that this has a finite limit, and we would like to know this number. Of course, we could run the algorithm for many sizes and look at it, but the question is, can we compute it? Heuristically or preferably rigorously? All right, so let's do what we came here to do. So we introduce the Boltzmann measure. Okay, it's depending on n and beta. It's 1 over z and beta when this is just a partition sum. Okay, so it's the sum of all possible configuration of spin. There are 2 to the n of them. So there is no way we are going to do this easily. And then we know that the minimum cost is given by this expression when I have added a 1 over n to lead to the correct limit. All right, now what we want here in the question is the value of the typical minimum cost. All right, so I don't want to work with something that depends explicitly on the h's. So one thing you want to do is to compute the average minimum cost. Now I need to add the expectation here, which is expectation over h's. Okay, so whenever I use E, the variable I'm averaging about is the disorder, if you're a physicist, or the quench disorder, and it's this field, this set of h's. Okay, so this is what we want to compute. All right, now this means that this object here, the log of z divided by n in expectation, is fundamental. And it's called average free energy. And this is what we are going to consider for the next, for everything that will be said today. Phi n of beta. All right, so the first thing we might say about this object is that asymptotically, the typical value of the energy is very close to its expectation. And this is why computing its average is good. We don't need to compute the typical value. We can just compute the average because they are the same. And it's very easy to show that typically the log of z over n is equal to its expectation plus something which is of the order 1 over square root of n. In fact, you can prove this in few lines. There are many ways to do it, but if you just apply the Gaussian Poincare inequality, you directly get that the variance of this random variable is bounded by 1 over n and the expectation of this derivative. And if you compute this derivative, you will see it's finite. So the variance is taken like 1 over n. Okay, now it's interesting. That's the reason why physicists really wanted to compute this average free energy. And they used to say this very nice word, the free energy is self-averaging, right? It's a quantity that when you sum n to infinity is equal to its average. And of course, in math, that is not what you would say. You would say that the free energy concentrates. Okay, but if you encounter this term, self-averaging, you mean it's just a form of concentration. All right, easy. So what we have to do is to compute this object. How are we going to do this? Well, it's not so easy because computing expectations is hard, but computing expectation of a log of a function is usually very hard because we don't have much control on, we don't have many integrals that involve the log. So in order to do so, we are going to use this one-fit-all tool from statistical physics called the Replicameter. And first, I will discuss it from the physics point of view. And you will see that I will do a lot of things which are really mathematically, let's say, daring or even wrong in sometimes, but it will be okay. And after this, we are going to see how we can do this and obtain the same result rigorously. All right, so this replica method is actually an old beast. It appears in statistical physics thanks to this man with Sam Edwards. And actually, Sam Edwards himself said that he learned it in a conference by this man with Mark Katz, the same Katz as Katz Rice and many other formula. And then it was developed in statistical physics into a very robust and versatile tool, especially thanks to the breakthrough work of Giorgio Parisi. And today, thanks to the work of Giorgio and Marc Mézard, we have a set of tools which is still heuristic, but we can use it to attack many, many problems and compute this average free energy. Okay, how does it work? So the idea is extremely simple, and you might even say trivial. And in fact, the mathematical difficulty comes here directly. So here is a trick. When n is very small, close to 0, expectation of z to the n is equal to expectation of n log z. But if n is small, you can Taylor expand, and it's 1 plus n log z. And so the expectation of zn is 1 plus n expectation of log z. Right? So of course, if we send n to 0, the expectation of the log is given by expectation of z to the n minus 1 over n. This is easy, and it's actually not completely crazy to write this. It's perfectly fine, even though you may worry about permutation of limits, but it doesn't sound completely insane. But this is not where the problem is. So here is it. So the way we do things is that we evaluate the expectation of z to the n for integrous values of n, because we know how to do it. And then we can interpret these copies, z to the 2, z to the 3, as replica of the same system. This is where the name comes from. And then this is when the craziness begins. Once we have the expression for any integral values of n, we somehow assume the expression can be analytically continued when n is in R, which actually is a very dangerous mathematical thing to do, and it's not well defined. Finally, once we have done this, we send n to 0, the small one, then n to infinity, large dimension, and we are also being very careless in the order of limits. And magically, we hope that this works. All right, so let's see how it works. Now, this is the part which is the most boring part of the talk, because I'm going to show computations. Now, usually I do this with a tablet or on the blackboard, but I don't have a tablet now. So I am doing it on slides, and I will try to be slow enough so that everyone can follow. Of course, all the computations are very simple, but it's usually hard to follow computations on slides. In fact, I'm always telling my students never to present computations on slides. So I will do the exact opposite of what I say, and I'm sorry for this, but I think we can all concentrate for these two next slides. All right, let's try to compute z to the power small n. All right, this is a definition of what it is. Exponential minus beta, this is Hamiltonian. This is the sum of all configuration, it's to the power of small n. N is integer. All right, the first change is that instead of taking this power, we say that it's a product of n copies, each indexed by a letter alpha. All right, and now what I'm going to show you is the way you will write this thing in any physics book. Okay, that's the way it's written in any replica computation that you will find in physics literature, and I think it's interesting to know how it's done in this community. Okay, the next step from here to here is to introduce a delta function. I'm summing over all m alpha, and I have a delta that makes sure that m alpha is equal to sum over I of Si alpha divided by n. This means that suddenly I can replace this term by this term. All right, the way the computation usually go, and this is a standard field theory trick that physicists use, is to say, well, I don't like deltas, but the delta are Fourier transform of the following expression. So I'm using the Fourier representation of delta. Right, so delta is replaced by the integrate over m hat, which is a very poor notation. because in statistics, of course, hat is an estimator. It's not this, but this is what it's used in physics, right? We write the delta, it's Fourier transform of this function, right? Now, why did we do this? Well, we did this because now the sum here can be pushed really here. And you see that we got rid of this nasty term here that was somewhat complicated. Indeed, now we can push this sum here. All these terms here do not depend on S. And now this hard computation, summing of the 2 to the n possible configuration, is reduced to this simple term. And that is for each replica. But if you look at this, you see that these actually can be factorized independently over all site I. So you can actually perform this computation, this summation over the 2 to the n configurations, and it's just giving you this simple term, product over I of 2 hyperbolic cosine beta hi minus I m hat alpha. Right, the whole reason physicists introduce this change here is to somehow arrive at a point where the impossible to do sum can be actually done in a very simple way. All right, now we did the hard part. It's time to take averages. So now we take the expectation with respect to this quantity with respect to H. Now, H, the disorder, is not appearing here at all. And so you can push your expectation inside here. All right, the expectation is the product of all replica of this quantity. And once you take the expectation, well, this product here factorize also. So it gives you this power n here. So actually, right now, we have not done so many, everything here is still okay. Actually, we didn't do any crazy mathematics for it. With a bit of effort, all this could be made rigorous, actually. But let's go to the next part. All right, so the next part is to realize that we still have to do this integral here. And it's a very complicated integral, okay? It's n dimension. And this is kind of funny because n eventually will go to 0. So, well, this is a weird thing. Now, this is where physicists look at this object and say, look, there is an exponential here of terms with a power n here. So this will be exponentially large. And so it looks like I'm going to be able to do a saddle point here. And if I do a saddle point, I will be dominated by some special values of these m hat and m's. Now, one natural thing to do is to do what is called the replica symmetric assumption. Let's assume that once I do this integral, it will be exponentially dominated by values of m alpha and m hat that are all the same. All the m alpha are equal to m, all the m hat alpha are equal to m hat. Interestingly, this is the part that breaks in more interesting computations. And in fact, we know that the replica symmetric assumption can be totally wrong. And the way to do a replica symmetry broken on that, to find the correct point that will be the correct saddle, is very tricky. And it was something that was understood by Giorgio Parisi, and he basically guessed it. And it was a major achievement, and it took physicists 10 years to kind of believe that it was a correct guess, and mathematicians 10, 15 more years to actually be able to prove it. We are going, I will try to avoid replica symmetry breaking. All right, so once you do this, well, this expression is much simpler now. It's just an integral over dm hat. This sum here is just giving you a small n here. It's repeated n. I'm still assuming that n is integer, so it's fine. This expectation here, well, this thing here is, again, they're all the same, so it's just a matter of putting a power n here, and we are something much simpler. All right, that's another step, which is very interesting, and I know that people reading for the first time the physics-style computation are lost here because they don't say it, so I will say it, so it is clear for everyone. At this point, what physicists do is to use, again, the replica trick inside the replica, right? Let's call this x. We have something here which is expectation of x to the power n. Now, we are going to say, fine, n is going to be close to 0. So we can use the replica again. And somehow say, well, the expectation of xn will be close to exponential of n expectation of log x. This is crazy, right? This is not something we should expect to be true in general. Of course, if n is going to 0, this is, I mean, it's a formal computation. But it's clear here that there is something weird. And in fact, when you see this, you start to think, if I'm going to prove this, at some point, I will have to care about the concentration of this variable, which actually turns out to be the difficulty. But never mind this. All right, once we do this, then this part is written as exponential. And we're almost there, because now we see that we have an exponential with n here. All right, now we somehow forget that the small n is small, and we say the large n is going to infinity, large dimension. So I can do a saddle point. If I can do a saddle point, I will be dominated by the extremum of this function. Here it is. Well, if I'm dominated by the extremum, I can compute for what it is. For instance, I can make the derivation with m, and I will find that the extremization is forcing I m hat to be equal to minus beta m. And finally, I find the following expression, which is the final one. So here it is. That's a full replica computation in a sample case, but it doesn't get much more complicated than this. It gets more tedious maybe, but the ideas are always the same, right? And now physicists will say, fine, now the expectation of log 0 over n will converge to the extremum of this function, which is written. So we have replaced the evaluation of the intractable quantity with something which is just, one-dimensional integral and a minimization process. So it's a trivial thing to do. All right, once we are there, physicists are happy. They are looking for the extremum here. It's easy to extremize this function. In fact, this is a fixed point condition. M star should be equal to the expectation of the hyperbolic tangent of beta h plus m star. This expectation is over the distribution of h. And then you can put this in a computer. For instance, here I use h with a variance 0.1. And I'm plotting here many plots of this function. See how it looks. It depends on beta. So when beta is very small, you have something like this. The maximum is at 0. When beta is larger, at some point, you start to see that there are maximum appearing here. And when beta is getting larger and larger, the maximum got closer to 1. And in fact, this is where the maximum is doing, and star, the maximizer is doing. And this point, where you have a drastic non-analytic behavior, is called a phase transition. Okay, this is exactly what phase transition here. Now, once you have done this, you can send beta to infinity, and we can finally answer the question we wanted to ask at the very beginning, which is what is the minimal cost? This is the variance of the random field, and here it is. Okay, if the variance is 0, it's minus 1/2. Obviously, it's what you get when you have all field together. And when you increase the random field, you can get actually lower values and until you reach this kind of linear behavior. All right, that's the full computation, and that's the way it's done in physics. Now, there are many reasons why you could doubt the validity of this computation. For instance, the fact that you do this crazy analytic computation continuation. And one of the interesting questions we may ask is, can we do all that rigorously? Can we do this from the mathematician point of view? And the answer is not entirely, but for some problem, we can do it. And it has been largely due at the beginning to the effort of these two persons. This is Francesco Guerra, and this is Michel Talagrand. In fact, Michel Talagrand has written many interesting books and made fantastic progresses on obtaining rigorous results for the replica method. Interestingly, no one was able to prove that the method is itself valid. Okay, that it's okay to go from n integer to n continuous and everything. In fact, I'm not aware of any result that is able to say something on the method. What people did was to say, fine, let's assume this is true. Can we prove it? And of course, it's always somewhat simpler to try to prove something once you're convinced it's true. So physics is giving you a good guess here. And the question is, can you prove it? Okay. So these are very interesting references in on the work of Michel Talagrand.
So
yes?
Are there things that the method would predict that are not known? So is the method somehow more general than the actual things which are known to be proven?
Yes, there are still many results that we don't know how to prove, and that will be discussed later on. There are less and less of them, but we are not going to throw away the method yet. Of course, this is what we all want, right? To throw away this and replace it with the principal technique. I think we are probably halfway there, but we are not there yet. And I will be discussing some open problem later on. Well, actually, Lenka will be discussing open problems. I will still be discussing simple ones. All right, let's see how we can prove this. Interestingly, you can do it rather shortly, and the techniques are the same one that can be used for more interesting and more complicated problems. So the standard technique to prove this formula is called Guerra interpolation. It's due to Francesco Guerra at the origin, at the early 2000s. And in fact, the way to do it for this problem, for exactly this problem here, it's something we worked out with Jiaming Xu and Lenka Zdeborova during our visit in Berkeley in the Science Institute 4 years ago. This is where I was starting to be interested by this problem. And so it's kind of nice to be back, even virtually 4 years later and to discuss about it. So here is how it works. We consider this new problem here, which is not exactly the random field problem because there is a small t here. Okay, so it's a kind of fake time indices between 0 and 1. And you have a m1 minus t there. Okay, so now of course I'm introducing the partition sum and the Boltzmann average for this new problem. Now the interesting thing is that when t is equal to 1, this goes away, and this is just the problem we want to solve. Okay, at t1, this is the random thing model. Okay, so phi n, what we want to know is indeed the expectation of log of z n t equal 1 divided by n. And what we really want to know is the limit when n is going to infinity of the survey. All right, so the way you do Guerra interpolation is by using, well, the fundamental theorem of calculus. And you just say, well, this quantity at t equal 1 is just the quantity at t equals 0 plus the expectation of the integral from 0 to 1 of the derivative with respect to t. Okay, and of course you have to be a bit careful with the expectation and integrals, but it's usually fine. There's no problem here. All right, now it turns out that these terms are easy to compute. The first one here, at t equals 0, well, this thing disappears, so it's a set of independent variables. So you can compute it, it's trivial. It gives this part. And this is nice because you can start, you recover almost what we want. If you have good memory, you realize that this is up to one term, the replica symmetric formula we are looking for. The second part is a bit more tricky. Okay, you have this derivative of log. If you remember, when you make derivative with respect of the log, well, you start to see Boltzmann averages appearing, and so you start to have this thing here, and you have this nasty expression, and we have no idea how to compute this, right? I mean, this is essentially the expectation of the average value of the variable at finite t. So for this whole problem, n beta. So we need to know it here. And then I need to integrate it. So I need to know it for all t. There is no way I'm going to compute this. I don't know it. Okay. But if you look closely here, you can start to see that it looks like a square. This thing is squared, and it looks like a cross product. So if we add plus m squared in front, well, now it's good, because if we had plus m squared and minus m squared, the minus m squared over 2 was exactly what was missing here to get phi rs, the replica symmetric potential. So this is exactly what is predicted by replica. And now the plus m squared over 2 is what you need to complete the square. Now we have the following. For all value of n at every number of variable in all dimensions, the average free energy is equal to the replica symmetric 1 with a value of m, which can be arbitrary at this point, by the way, plus beta times the expectation of this quantity. And of course, the first thing you should say is, well, this is a square, it's positive. So obviously, this is going to be larger than that. And we have a lower bound to phi n, which is valid for all n. Okay, and that's typically what was obtained by Francesco Guerra in the early 2000s, even though he did it for much more complicated problems. And, so did we with Jennings, but here you can see it in a few lines, and I think it's an interesting example. So getting a lower bound is rather easy.
Is this just, I mean, did it just coincidentally work out that you could complete the square, or is there some like deeper reason that this worked out?
To be fair, I don't have a good intuition. It always kind of works, except that you don't have always squared. For instance, you might have a power 3 or a power 5, in which case it's slightly annoying and you have to think a bit more and to try to use other trick. In fact, when you do the famous tensor factorization problem, you know, and the tensor of order P, you have a P here, so you cannot use this technique directly. However, it always looked like something like this. And by the way, we know that M is supposed to be, it's supposed to be the magnetization, which is a typical value here. So if this thing concentrate, well, it looks as this is going to go to 0. So it looks right. But of course, to prove it is another story.
Thanks.
All right, how do we get the converse bound? And this is the one which is usually harder, and there are many tricks to do it. I will use here one trick which I learned from Ahmed El-Alawi, actually in Berkeley as well. And it's an interesting trick because it allows me to introduce another quantity, which is a constraint free energy. All right, now I'm going to use this object, the constraint partition sum, where I'm summing over all configuration. And I'm putting an indicator function saying, look, I will keep only the configurations when the sum of variables are equal to n times small m. Right, and of course, then you need to put this indicator function into expectations, and you can define, now, why is this interesting? Well, if you sum over all m, this quantity, of course, you have the whole partition sum. Okay, so the constraint partition sum at finite m gives you the relative weight of configuration with magnetization m. In fact, it's a way to set up a large deviation principle. It's exactly what can happen. All right, now it means that phi n, which is expectation log of z, is really the expectation of log of z sum over all possible value of m of the constraint magnetization, right? So this thing has a clear meaning. All right, why is it interesting? Well, let's forget about this for a while, and let's consider the constraint free energy. Okay, so this is a log of z constraint at a magnetization m. All right, and now we are going to do the Guerra interpolation for this object, the constraint free energy. Okay, it's totally easy to do it because these are the exact same computation that we did, except that you have an indicator function. So the constraint free energy is the one at t equal 1. It's equal to the one at t equals 0 plus integral of the derivative. Is just that now we have these constraints here. Okay. Now the first part, this one, well, the first thing you could remark is that obviously the constraint sum is smaller than the total sum. So the expectation of the log of z m is certainly smaller than the expectation of log of z. So I can just say, well, look, I will not compute this. I will just bound it by what we had before. I could, of course, compute it, but I don't need to. Good. And then the second part, well, it's exactly the same as before, except now, well, I have this measure here, which is constrained to value m. Okay, next step, just to complete the square, and we have the same thing as before, except now that we have a low, we have little equal here. But now this is where it's very interesting, because here we have this m minus sum over I si over n, but this average is considering only values when sum of si over n is exactly equal to m. So this is going to 0. Okay, and we have this very nice result, but the replica function is an upper bound to the constraint free energy. Actually, we kind of believe that this is true, maybe not at all n, but asymptotically, this is what we actually believe to be fully generic in the replica theory, even though I don't know to prove this in full generality. But here it's true. Okay, the constraint free energy gives you a lower bound. Okay, the constraint free energy is a lower bound than the replica, and the replica is an upper bound than the constraint free energy. All right, how are we going to use this to finish the trick? Well, at this point, it's very easy, and it's again something that was understood by Ahmed. You just say, well, phi n is the log of z, but it's the log of sum over m of log of the constraint, partition sum. Then you just say, fine, I'm going to bound this by just keeping the max. So just there are two n values that n can take. So I will just say it's smaller than 2n times the maximum one. Now there is a tricky part because the maximum here can change a bit when the disorder changes. So it can fluctuate from sample to sample. So you have to prove that it does not. And it's very easy. It does not because the free energy concentrate. And once you do this, well, you can essentially write this. And phi n, the true free energy, is bounded by the constraint free energy evaluated at its maximum plus something which is order 1. I mean, it's log n over n goes to 0. All right, so this is what it means in a nutshell. You have to do this a bit more carefully than what I did, but this is what it really means. All right, and once we are here, well, once we are here, that is already a nice result. And finally, we have both bound, right? That's what we had from the direct Guerra interpolation. And using this trick, phi n is smaller than the constraint one, which is instead smaller than the replica symmetric one, and we have both bounds. And when n is going to infinity to 0, that is, sorry, when large n is going to infinity, this is going to 0. We have a perfect sandwich, and we can take the limits, and we finally get the rigorous result. Okay, and this is it. And that's one way to prove this formula. I just want to mention that there is a very interesting, much more challenging scheme that has been developed by Jean Barbier and Nicolas Matris to tackle similar problems in a more complicated setting. It's called the adaptive interpolation scheme. It's much more powerful than what I'm showing here. But in this paper here, this paper on archive, they show exactly how their scheme works for this simple random field Ising model, and it's I think it's a very interesting exercise to understand how it works before moving to a slightly more complicated problem. All right, now we have seen how replica computation goes. We have seen some of the standard technique that we have to prove them, but we have just seen evaluation of free energies. All right. And we want to speak about computation and algorithm. So let's discuss algorithm. And in the physics community, what we really love is iterative algorithm, when you just iterate the same equation many, many times. Now, that could be a whole class in itself. And so I will just do a very brief description. And again, it turns out that for the random field Ising model, you can do things trivially. Okay, so let's do it. All right, let's say that what we want to do is to find the marginal at finite beta. We want to sample. We want to find the expectation of Isai for a given problem. Well, the favorite algorithm from physics is certainly called mean field. It was developed for this problem by Pierre Curie and Pierre Weiss at the beginning of the 20th century, and then it made its way to machine learning. There is a beautiful review by Wainwright and Jordan. And if you write this very naive algorithm here, this is what you get. It's telling you that maybe what you should do is to take your estimate of the marginal probability. By the way, you just need the expectation to completely characterize the distribution of a binary variable. So you just need to know mi. So mi at time t plus 1 is the hyperbolic tangent of beta times hi plus the average over all the marginals. Okay, it's extremely simple iterative equation. In fact, we are lucky here because for any other problem, this thing becomes messy, but this is what it is. Now, if you think about what this algorithm is doing, and you want to say, okay, I want to know what it is doing. I want to track its progress. And it's very easy. You can write the equivalent of state evolution here. So if you define m of t, which is the value of the average value in your sample of the marginals, it's trivial to see that m of t will follow the following equation, right? I mean, this is m of t. This is all M at the next step. So asymptotically, when you have a large system, you are just taking the expectation over H. Yeah. And this is what you have. Right? So it's interesting. You can entirely understand what the algorithm is doing by looking at the scalar equation. All right. So why is this interesting? Because this scalar equation here is exactly the same that was giving you the maximum of the replica fixed point. Okay. And this correspondence between trying to follow what iterative algorithms are doing in this problem in large dimension and saying that they are trying just to find the maximum somehow, they are really moving on this replica potential and trying to find maximum, is something we find all the time. And that is actually at the root of our interpretation of computational hardness in this community. All right, so let me briefly conclude what we have learned here. What do we have? Well, first we had this replica potential. We derive it heuristically, then we show to prove it. And the maximum, or at least it's extremum in general, but here it's a max, gives the value of the correct free energy. You can prove it. We have this interesting connection between the constraint free energy and the replica potential, right? We actually saw that the constraint free energy is a lower bound to the replica potential for all M with equality at the max. And finally, it was very easy for this problem to derive an iterative algorithm whose behavior is connected to the fixed point of the replica potential. All right, but that was for a very simple problem. So why is this interesting? So the reason this is interesting is that the exact same 3 points can be made true for a very large class of problems. And that's basically everything we are going to say in the next 3 lectures. Many minimization and sampling problem on complete graph, random graph, diluted graphs, and so on and so forth. A large set of problems, when you study with that kind of techniques, you find these 3 points. Sometimes you're not able to prove them, but at least heuristically, this is always what we find for a large set of problems. And so I think I thought it was interesting to show them how it works in this somehow simple and one may say even trivial example. Okay, and that's what we're going to discuss in the next lectures. And I will assume that now you are expert on this, so you will know everything. All right, so now for the last 5 minutes, I just want to give an exercise to those who want to check they have learned everything. A good exercise is to try to repeat the exam side computations, that is the replica derivation and interpolation type proof for the spike matrix model. So what is the spike matrix model? So here it is. Let's say that you have a generative model. So you have a generative model, you have a distribution for a vector x star. You sample x star from it. Let's say that x star is a vector in n dimension. So for instance, it can be on the sphere, it can be IID Gaussian, or it can be each of its components can be Rademacher, whatever. It can actually even be a complex, not factorized distribution. And now you are observing Y, which is an n times n matrix, a symmetric one, mind you, which is defined as follow. Yij is 1 over square root of n xi star, xj star, plus the Gaussian random variable. Okay, you are looking at a noisy version of this product here, which in fact is just a way of saying that Y is a symmetric matrix, that is the sum of a random symmetric matrix, that we know very well, plus this rank 1 matrix, which is what is called the spike. All right, and the kind of question you might want to ask here is, if I'm giving you Y, are you able to find back a good estimator of X star or not? So there have been tons and tons of problems and discussions and articles and works on this problem. I believe it was introduced by Johnson and Donoho in the context of signal processing and also statistics. All right. Now that problem can be set up into a probabilistic model. Well, you just need to find what is the posterior probability of X given Y. Well, it's the product up to normalization of the likelihood times the prior. The likelihood, well, this is just a Gaussian. So you can write an Hamiltonian, which will not be too complicated. You see, you have this quadratic term here, and then you somehow have to deal with the prior. If it is complicated, it gets more messy. Then what we know from Bayes' optimal estimation is that the best estimator, at least if you want to minimize the mean square error, is given by the posterior mean. Okay, so you need to compute these averages. All right, so if you repeat the exact same step that I have shown you for the random fingerling model, for that problem, it's slightly more complicated, but not too much. This is what you find. First, you can repeat the replica computation physics style, and it tells you that you can compute the free energy here, and the free energy tells you that you need to compute the maximum of replica potential, and this is how it looks. All right, it's slightly more complicated. You have a two-dimensional integral and a three-dimensional one if you count this one. But all in all, it's still a very simple object. And we also know that the maximum of this function, m star, at least this is what we know from the replica computation, is telling you what is the best overlap you can get if you try to solve the Bayes problem. In fact, the optimal error is 1 minus m. You can repeat the Guerra interpolation in this problem, and this is what it gives. The same kind of result we already saw. In fact, this is where we developed these techniques here. So this result here was obtained by jamming when we worked in Berkeley together 4 years ago. And the this overbound was much more tricky. I think we first got it in a very complicated way in this paper with Barbier, Diam, Chris, and Lenka and Thibault. A much nicer proof was then found by Lelarge and Yolan, which was much shorter. Then with Ahmed, we decided that we wanted to be even more short, and we used here the proof, which is exactly using what I told you a few slides ago. So it is really using this constant free energy. And then very recently, there is again another proof that was shown by Jean Barbier and Nicolas Macris using this very clever Guerra interpolation. Anyway, if you repeat what is in this paper here, you will get this, which allows you to prove this statement. And I didn't write it, but it also allows you to prove that M max is the Bayes optimal overlap. What about the third point? Oh yeah, sorry. And for those of you who are interested, the full derivation is written here. And if you don't want to copy this ugly list of characters, you can just go to the set of notes that I left from our Duke lecture note, and it's in chapter 6. All right, the third point was iterative algorithm. And that's interesting because you need to work a bit more here to get an iterative algorithm. It's just not mean field. In fact, mean field is not correct. Mean field will give you this part, but not that part. And this is called the Onsager term. But anyway, you can work it out. It's called approximate message passing. In fact, it was called the TAP equation from Thouless, Anderson, Palmer in physics, even though physicists never thought of it really as an algorithm. And then it was developed in the context of compressed sensing first by Dono, Montanari, and Malecki like 10 years ago. And there have been a lot of work in this direction. And for the SPAC matrix model, it was written by Sandeep Rangan and Ali Fletcher. All right, this is how it looks. You have an iteration here. This vector are iterated with respect to A, which has estimation of the marginal. These are estimation of variances. And anyway, so I'm not going to enter into the detail because I will discuss this later on. But the point is, you can write a state evolution again. You can try to track what the algorithm is doing. For instance, if you want to know how much your estimate of the X star correlate with X star, so how much the overlap, well, you can define M of t to be the overlap between your estimate at MT and X star, and you will find again that M of t is following a sample recursion. And if you look closely enough this recursion, well, you will realize this is exactly, again, the same as a fixed point of the replica potential. Okay, so this seems to be something that we find all the time. But these algorithms that we like IMP and belief propagation, they are just trying to climb the replica potential. And this is again, something that we're going to use later on. All right, so that's all for today. And that was sort of a review of the statistical physics methods that will be part of, of the toolbox that was used to derive many of the results that will be discussed tomorrow and the next 3 days. Let me again mention that additional material, notes, and exercise, including the full correction of the exercise I give you, which is quite the replica theory and proof for the rank 1 problem that we found here. You just need to go to my webpage and there is a link, so you don't have to copy it. And again, I want to make a shameless advertising of our review with Lenka. All right, so I think my 1 hour is basically up. So it's probably a good moment to stop. And I thank all of you for your attention.
Thank you so much. So there are a couple of questions in the chat. So there's a question from Renee Carmona. Can you read it, Florent?
All right, let me go through the chat. Okay, chat. Why am I here?
Renee, you can also unmute yourself, I think.
Yes, so I just unmute. So my question was mostly about historical. I thought that one of the early proof of the mathematically rigorous early proof of the replica trick was done using non-commutative integration theory and recasting the problem as a Fermion problem. I have very vague recollection from the mid 85. So is that something different, or is that something similar? These were worked by physicists like Abel Klein.
Yeah, it rings a bell. I'm not familiar too much with this work, so I'm afraid I will not be able to really give an answer here. But I can look it up and try to give you a more informed opinion tomorrow. I mean, there have been a lot of work on these techniques. So I am mentioning very few of the things that have been done for the proof on replica. I don't know about this one. I mean, I sort of, it rings a bell. There have been also amazing work by Michael Eisenman in Princeton. There are many techniques that have been used. These days, what people have been, using to make the real breakthrough is certainly the interpolation, and that's certainly what was used by Michel Talagan. But I can look it up. Thank you. Give me the reference.
I have a question about the replica method that you presented earlier. So for many interesting models, I guess for any integer n, the expected value of z to the n will be much larger than the typical value of z to the n.
Yes.
So then in such a model, when you apply the replica method and you compute the value at the replica symmetric saddle point, will that be correct for integer n or no?
That's a very good question. I'm not even sure. Maybe, I mean, that's a good question. I think I would say that it should kind of work. I mean, I remember that once you look at the continuous value of n, you start, I mean, a good exercise to look at this is the random energy model, which is of course totally trivial. And I remember when you go from n large, and when it goes below 1, actually things are okay, and then you have a phase transition at some point. So there is certainly, I would be willing to bet that there is a finite value, even a continuous one in R of n, such that for all n larger than this one, things are perfectly correct. Yes, I think you are right. I don't see why phase value should be between 0 and 1. I think so too. Yeah.
I see. So the heuristic computation
something funny is happening. Yes.
I see. So the heuristic value of the integral can be correct even if the...
Oh, yes. I think, you know, what we do at finite n is not totally crazy, except that we use these deltas and exponential of, you know, in the Fourier representation. But even this is not particularly, you know, I think with a bit of effort, this thing can be made okay. It's really when you start to take this crazy analytic computation n going to 0. I mean, of course, it doesn't make sense mathematically, right? I mean, the small n going to 0 while the big N is going to infinity is totally insane. I mean, even the saddle point is weird, right? Because I'm, you know, when I want, I'm saying, oh, small n is small, and then large N is big. And then we should start to worry with the velocity to which, you know, the ratio is going to, I don't know. I mean, the more I think about the method, the less I understand it. In fact, myself, I like much more, as you know, the cavity method, which allows you to get the same kind of result. And it's still not rigorous, but at least the hypothesis is on the table, right? And so you know what you do. I was very enthusiastic
I also
with the
wanted
Replica
to
method,
ask,
but you know, I'm not sure I understand it. It's still a bit magic for me.
so
For
are
many of
there
my
examples of things that you can only get from Replica and not from cavity, or vice versa?
I don't think so. I think there are examples of things that you get with less computation with cavity and some that you get with less computation with Replica, right? Sometimes, you know, for these fully connected problems in complete graph, computation are usually shorter with Replica. So for instance, if I try to do the cavity for the random optimizing model, I think it will take me maybe a few lines more. As you well know, if you try to work on diluted random graph, you know, Erdős-Rényi graph, coloring, and all this stuff, this is really hard to do with Replica. In fact, you know, all this work that we did on SAT and coloring and everything, people in physics did it first with Replica. And they obtained the same equation, but it was so long, you know, it was pages and pages and pages. And after 10 pages, you arrive to what you get from one, you know, first page from the cavity method. So, you know, it's really more which one is a more you know, is a better or, you know, shorter heuristic to get the truth. But as far as I know, anytime we try hard, you know, every time we try hard to use the two methods, as far as I know, they always coincide. So I don't know of anything when they disagree or on problems where it's not possible to use one and not the other. It's more that it's more practical to use one with respect to the other.
But
Hi,
there's
Florent.
no...
Oh, sorry. I have maybe a comment about that. So Florent,
Please.
can you get finite size effects or fluctuations using the replica method? I know you can get them with the cavity, and that's how you can prove many results.
Yes, you can. And it's even more crazy. So what you have to do is to make the correction in finite n, small n. All right, and the small n correction, so the correction to n to 0, so I let you imagine what it means replica space, because obviously it's going to be a mess. You can connect them to fluctuations, finite size effect, and I mean, certainly fluctuations for a start. And again, that was something that Giorgio was pushing for a while. And of course, it leads to, it was, of course, very, very hard for mathematicians to say anything on this. I think really mathematics started to progress in this field when the cavity method was introduced, because suddenly things made sense. And you know, the Eisenman SimStar scheme is all about cavity. And I mean, somehow the Guerra interpolation is a totally different beast. You know, we could also entirely forget about replica and try to do a non-rigorous Guerra interpolation, and probably we can get all the replica results. The trouble with the Guerra interpolation is that, you know, I cheated a bit here. I use a sample case, but in reality, you have met, you know, as you well know, actually, Ahmed, you have a lot of terms, and then you have to work really, really hard to prove concentration, and this is tricky. And if it is not in some book by Talagrand, then usually we are lost.
So there is one question maybe that you didn't answer when you were doing the computation. So when you write extremum or extremization, there is a freedom of choice in terms of which saddle points you're going to choose. And sometimes you have to choose the right branch. Can you comment on that?
Yes. So if you want to do it cleanly, it's very easy. You know, you can just break the symmetry by adding a small term, and that's what, you know, it's actually an old trick in mathematics. That's the way people were defining deep states, and so that's usually not a real problem. But of course, it's one of the problems we have when we want to prove things. Because, for instance, I said, well, obviously M is going to be equal to the expected, you know, to its average. Well, that's not true, because what M will be, you know, the distribution of M, strictly speaking, is, you know, two peak, one at plus M and one at minus M. One of the nice things that you can do with the constraints free energy, actually you did this, is to start to prove exponential concentration over one peak or two peaks. But usually this is, you know, something that we have to care about. We have to break the symmetry, and then we have to care about, you know, how the limit is taken. And once you do this, a lot of things bad can happen. And you know, again, you know, everything is okay for the random optimizing model. Everything is okay for the rank 1 model. And once we go beyond this, we start to have difficulties.
Maybe I can ask
one of these. Yeah, please.
Well, I was going to ask a question that's a sort of like a more zoomed out question, which is, so, you know, you showed us the analysis for this, you know, Curie-Weiss model, but under what conditions should we expect these sort of methods to be successful? Like,
oh yeah,
you know, you can imagine if the Hamiltonian is really non-smooth or something, that things would go really wrong. So I mean, can you maybe give like a sense of the scope of this approach?
Yeah, you know, and I wish I had a very perfect good answer to this. You know, it's sometimes more of an art than a science to guess in advance when it's going to work. I mean, you know, physicists will tell you, well, it always works when the mean field approximation is right, but it doesn't mean anything because, you know, it's just saying that it works when it works. And so far, it works at least if you have, you know, kind of homogeneous problem, and you also need to have the free energy written in a way that its limit exists, which is actually a very important problem. One of the reasons IMP is breaking for a problem like tensor factorization is that tensor factorization in this regime where, you know, SDP is working and is a regime where actually the physics computation is entirely crap. And if you want to correct this, you have to work hard from physics. And again, we have to thank Ahmed and Chris and Alex for this. And I will probably comment on this. But one of the first things is this one. Well, we need to be in a very nice regime. We need to have the high dimensional limit such that things converge to a scalar. You know, the free energy should be here, should be well behaved, should concentrate. And then I think that, you know, it's most that we need to be able to do the computation. And to be able to do the computation, well, we cannot do very complicated things. You know, this is where things should be homogeneous enough so that we have nice integral that we can do. Now, if you start to have things which are very heterogeneous and, you know, some kind of couplings, we have a weird distribution with fat tails. Well, I will not trust the replica method with my life in this situation. I mean, I will be willing to give it a try, of course. But,
so if you're on a grid, for instance, for City, if your interaction is on a two-dimensional grid, there's no way the replica method is going to work.
Well, it's not really that it's not working, actually. It's just that we have no clue how to compute anything, right? I mean, we don't know to compute the, you know, we don't know to compute these moments on the grid. Maybe if we will be clever enough to compute, you know, all the, you know, integral moment of Zn and find the correct ansatz of minimizer or during the saddle point, maybe it might work. We just have no idea to do it. We just have absolutely no clue to do it. In 1D, we can do it. In some 2D problems, somehow we can do it by, you know, cheating a bit. For instance, this is what some of my friends doing quantum computation, we talk about fermions. Fermions, it's sometimes a way to add a dimension. But yeah, we have no idea how to do this thing on grids. Absolutely no ideas. But it's, I don't know if it is because the replica method is wrong. It's mostly we have no idea how to do the computation.
I see.
So, I think the answer to your question is, if I'm able to do these computations, I'm willing to call the results a clever conjecture. And mostly the problem where you cannot apply it is the problem where you have no idea how to apply it because this is too hard.
Sure. Okay, thanks.
Okay, we have one more quick question from the chat. Someone asked, can you comment on how to design the interpolation path?
Oh, very good questions. Well, again, if there is, what we really would like to have, I think the problem will be solved from a mathematical point of view when we will have the answer to this. When someone will write a book saying, okay, for this problem, this is the interpolation scheme, then you have to work out to work and you get the answer. Then I think we can just forget about the replica method. We will have a perfectly principled mathematical setting. Right now, you need to be imaginative. In fact, the book by Michel Talagrand is showing a lot of imagination into ways how to do this smart path approach. And recently, there was this very nice paper by Jean Barbier and Nicolas Macris that was then further used by Leo Miolan, when we used it to prove some results. And here, what they use is to say, why do you use a scalar m in the interpolation? You can use a function m of t. And then you start to have a lot of freedom, and it's extremely powerful. You can start to prove very complicated results with this. But to be fair, it also becomes mathematically much more difficult to have everything under control, because then suddenly you start to say, okay, now I have a function m of t in my interpolation path. This function will be the solution of a differential equation. But then you have to worry if your differential equation has a solution, you have to prove it's unique. And then you realize that oh yes, but Ahmed told me that I need to break the symmetry, so you need to break the symmetry. Oh, but maybe by breaking the symmetry, I'm killing the solution, so you have to worry this is not happening. Then it's okay, then, and then you need to send this thing that breaks the symmetry to 0, and that also can hurt your solution. So this tool, the adaptive interpolation, is an extremely powerful tool, but it's also very delicate to use. But I think it shows that there are a lot of unexplored directions into the interpolation scheme. And well, I would say that, use your imagination. I mean, of course, one way to help you design the interpolation scheme is to know in advance the replica results. And the thing that look ugly in replica, you say this is what your interpolation should give you at time 0. And the part that looks okay, you hope it will pop up when you integrate from 0 to 1. But it's more of a guesswork than an exact tool right now.
Okay, I think we have time for one more quick question, and I think Anirudh has the question.
How do I ask it? Hello?
Yes, I hear you.
So my question was, I saw that you have written papers trying to do the replica trick on neural nets also.
Oh yes, well, it's not me. That's one of the first applications of the replica method, and people were crazy about this in the 80s. There have been tons of work on very simple nets, and of course now we would like to use this for more complicated nets.
So recently I saw 2 papers where you have tried to use replica method for neural nets, but I felt that it is somehow not working for the ReLU gate. Am I right in my understanding that the replica trick is not?
Say this again. You went off at some point.
I think from the paper what I got was that the replica trick is not working with the ReLU gates. Is that correct?
Well, I don't know. I don't see why. I mean, maybe computations get more complicated with rules, and so you know, you might not be able to get answer. But I don't remember. At least I never wrote this.
So that's what I felt from the paper, that some of the assumptions excluded the ReLU gate. If I was wondering if you have any comments about why the ReLU gate.
Okay, maybe. I don't know. I mean, you know, but it's like the answer to Saclay questions. You know, sometimes it's just that you have these computations, you do them, and you realize that things are much nicer if your activation is even or odd or something, and you restrict to this because it gives you nicer formula. So I think if we did it this way, it was just because we wanted to have nicer and simpler formula. But I don't see why the ReLU gate should be any problem.
So I wanted to get your comment on what is the long-term view there? Like, if you could get the replica trick to work on neural nets, what is the end goal there would be? Like, what would you be able to hope to be able to say about neural nets from replica?
All right, that's a great question. But I think this should be reserved for Lenka Zdeborova, because she's probably going to talk about things like this. So I will let her answer in lecture 3 or lecture 4.
Okay.
But the answer is that we have a vision of what we would like to do with it.
Okay, you have a one-line statement. What the end goal of replica trick on neural net is?
Oh, like well, you know, there are many things you might want to do. I mean, one of the things is, of course, to try to understand the landscapes of these objects. That's the line of thought around, you know, Gerard Benarous's vision. What we would like to do is to say, well, can we compute the generalization properties for a large set of problems without actually running an algorithm? Can we help design nets? Can we understand when it is easy and hard to train the net for such and such data, that kind of thing? This is really our long-term goal here.
Is there a concrete formula known, like replica trick working on neural nets implies something about the generalization error or the landscape? Is
sure,
there
are things that we know, but only for 2-layer networks now. So what I don't know if you call this a real.
Which paper can I see this formula?
I think Lenka is gonna talk about part of this. So give it one day or two, and
okay. Thanks a lot for the discussion.
No problem.
Okay, thank you so much, Florent. So I think we'll end here so that the next speaker can get set up, and we have a reception on Gather Town for the next about 10 minutes. So we'll see you all soon.